Okay, in this video, we will take a look at a special property of mirrors. So for my activity, these are the required materials. So first, I got this pen and as well with this mirror. Let's get started. In here, we are moving the pen back to front. And while we move the pen, we apparently get the same look. Meanwhile, let's consider the distance of the object from the mirror and the distance of the image behind the mirror. Actually, it's based from our knowledge that the distance of an object from the mirror is always equal to the distance of the image from the mirror. So here I have got a scientific way to figure this out. I just had drawn a ray diagram for the activity that we had done from the beginning. Okay, so let's get started. In here, we have a point object A in front of a plane mirror. And as we already know how to make images by just using the ray diagram, I just did it real quick. So first, I'm using one ray that is perpendicular to the mirror itself, and also another random ray, which is this one. After the reflection of the two rays, they meet at a point B, so B is the image of point A. I named the points over on the diagram itself. So the intersection of the line A and B with the mirror, I called it O. And the point of incidence of this ray on the mirror, I called it P. And the reflected ray, PC. Okay, so we have to prove that A is equal to BO. That's the distance of the object from the mirror is equal to the distance of the image from the mirror. We have to prove that AO is equal to BO. In this such a tricky time, I always use a trick. Here our goal is to show that AO is equal to BO. So that's our exit. Let's assume for a moment that AO is equal to BO. And let's see where it leads. If AO is equal to BO, then this line, OP, becomes the line of symmetry that is going to be between A and B. So all the points on OP will be equidistant from A and B. So P will also be at equal distances from A and B. I can say that AP is equal to BP. Now, in these two triangles, we have already assumed that AO is equal to BO. And with that, we showed that AP is equal to BP. And the third side, OP, is common in these both triangles. So I can say that OP is common to both triangles. So all the three sides becomes equal for these two triangles. Now we can say triangle AOP is congruent to triangle BOP. So it's AOP is congruent to BOP. Now we aren't sure whether AO is equal to BO. We have to prove that. So I can say if AO is equal to BO, I get triangle AOP congruent to triangle BOP. In this case, AO equals to BO. Now, how to prove these two triangles are congruent? So when you look at AOP and angle BOP, they both are 90 degrees. And OP is common to both, and also this line is common. What about these angles right here? These angles. Now, I have to prove that angle APO is congruent to angle BPO. So to prove these two angles, I need these angles. So if I can prove these angles are equal, then I can say that these triangles are equal or congruent. And if I can say that these triangles are congruent, then I can say AO is equal to BO. How to prove that these two angles are equal? So this is the incident ray, and here is the reflected ray. Angle of incidence, which is this, is AP, and this is the normal, which is NM. So APN is the angle of incidence, and APC is the angle of reflection. NPC and BPM, they are opposite angles. So all these three angles should be equal to each other. So angle APN and BPN are equal to each other. And also this big angle, which is OPM and OPN, are 90 degrees, as you see here. I drew it. So both are 90 degrees, these two. So angle OPN, I have written it over here, OPN equals to angle OPM is 90 degrees. And as first we say APN is this, APN is equal to BPN, sorry, not M. Here is N. All right. So now angle APO is equal to angle BPO, which is this. APO is equal to BPO, like this. And also, as we say, OP is common. Here also, then angle AOP is equal to angle BOP. And this is also 90 degrees. We have mentioned it right here. And then at the end, triangle AOP is congruent to triangle BOP. Here, angle AOP is congruent to triangle BOP. Here is triangle, yeah. Then we know that APO is angle APO is congruent to BPO is equal to triangle AOP, which is congruent to BOP, right here. Then at the end, after trying to know the angles that are equal to each other, we say AO is equal to BO, sorry, and here we write it right there. So we finally proved that in a plane mirror, the distance of the image is always equal to the distance of the object in 4 trials. So as you see in here, the one in left side, we discussed how to think and approach this problem. So basically, I didn't jump to the formal proof in the beginning, so it will be understandable in this way. I made 2 ways. So here is just the checkpoint, and here's the real way. So I just added these 2 so that you can understand more about it. Then we can also be sure by using this to get this overall. So at the end, we proved that in a plane mirror, always the distance of the image is going to be equal to the distance of the object itself, as in 4 trails. Okay guys, as you have seen my quick video of drawing this diagram for the reflection activity. Now first, before I start, I want to show the materials and the requirements that I have used for this activity. So starting up, I used a mirror for the reflection, and as well as 5 small oval shaped marbles. Okay, so first of all, what I had done is that I used a ruler and also a protractor. So the reason I used a ruler is that I had to measure first the mirror in order to know the measurement, so I can draw it on my paper and make a diagram in order to see the reflection of the marbles. So first of all, in here in the middle of the page, I drew a 16 centimeter for this mirror that I have, and I drew it over here so I can place it. So when I place it, overall I can see the marbles when I also place them there to see the reflection. Okay, so I use the letters in here to label them, label each part, so it will be easier for me. So in here I have letter E, in the middle, in the center is G, and also F in this side. And this is the reflection where it shows. Okay, So starting up, when I place the mirror, I want to check whether the marbles that I'm going to place will show the reflection correctly. So I have to check. So here's the point that I had done, and here's the other one. So I placed the marbles so carefully in order that I won't miss any parts of it for the reflection. So I'll place them right here in the points. Now I have to place it a bit here. Here we go, and this has to go to here. Okay, here we go. This is perfect. Now, as I had placed, this is the exact measurement. Now, as you see here, this line completely looks straight if you look at the mirror, and as well as the marble here. I don't know if you can see it, but still it shows like straight. From one side goes to the mirror, it shows the image there, and from the other side, it also shows the same thing. And in here that we have, when I was looking at the reflection, right? Okay, so I have already pointed out in here the marbles that I had placed so that it would be easy for me if I want to check it again. So we don't need these materials anymore. We're gonna use this because as you see here, the reflection, I first took a measurement of this and I used the protractor first so I can see it. Okay, so with the protractor, I used it to see 90 degrees here. So I can draw a line from here and put a point and continue till the end. So here's the point where we can see the marbles getting reflected. And then I again use this to like see from the side where I look at the mirror in order to see the marbles getting reflected. So I used the protractor like this. I measured first of all this small part, this part, and I got 30. This is the R1, is a reflection of 1. I got 30 degrees and I drew a line here and I labeled it as R1. Then secondly, I took a measurement of this whole line because it's getting reflective like this. So I used it again, I kept it here and I I actually didn't minus it, but I added both of these. So both of them I added, I got 60 degrees from the whole place. So the whole place, it reflects to us. Then to get the exact reflection, I use the OI, which is the incidence, equal OT, and the time where it get reflected. So in here, what I did is that I minus both of the degrees that I got, which is R1, 30 degrees minus R2, 60 degrees. And I got a final answer of 30 degrees. So this is the activity where a reflection is shown. And we have already observed the reflection by putting the marbles near the mirror, and you see it get reflected. You see, like from this side it goes straightly, from here it goes to the mirror, and you see the same lines here, it goes straight. And it happens with the same thing but over here. It's because of the reflection, the mirror reflects it, and from one startup point you can see the reflection. In this video, we're going to talk about the refraction and also to find the angle of refraction. So I use a protractor and also a ruler to measure my angle and as well as the block itself. So what exactly first is refraction? So refraction is the bending of the path of a light wave as it passes across the boundary by separating the two medias. So why is it caused? It is caused by the change in speed experienced by a wave when it changes in medium. So in this method, we see that the light ray refracts the most at the air glass boundary, and this is evident by the fact that the difference between the angle of incidence, which is this, and the angle of refraction is the greatest for the air and glass boundary. Refraction is a change in light speed, first of all, and wherever the light speed changes the most, the refraction is the greatest. So in here, First of all, we use a protractor to find the angle, and we got a 50-degree here. And in order to calculate and use the Snell's law, I got the index of refraction of air and also the glass. So air is 1 and glass is 1.5. Second thing we did is we use the Snell's law, which is sine incidence, angle of incidence equal or to sine angle of refraction. So we use sine angle of refraction. We corrected the formula in this way, and we use the inverse function for sine, and still we got the same formula with brackets on. So we use sine here with the angle here, but we got 50 degrees with sine. So what I first did is that our N1 was air and our N2 was glass. Basically the air and N2 is the glass. So what I did is that I replaced the sine of angle of incidence with 50 that we got, and N2 was the glass. So what I did, I got sine 50, the answer was 0.76 when you calculate with your calculator. And once I got that, I divided with glass and I got a matter of 31 degrees. So in this example, what happened is that the angle of refraction would be a measurable quantity that would indicate the amount of refraction taking place at any boundary. So it's actually a comparison of the angle of refraction to the angle of incidence that would provide a good measure of the refractability of any given boundary. So the angle of refraction here is more dependent upon the speed of light in each of the two materials that we got right here. So the speed is in turn dependent upon the optical density and the index of refraction that we have here, values of the two materials. So we used the Snell's law in order to get the final, and the final is 31 degrees. So we know that it takes 31 degrees to refract from air to glass. Thank you.